Hello guys, welcome to my YouTube channel Math Squad. So in this video we are going to see the examples which are given in your textbook before the exercise 1.1. So the first example is like this. Use Euclid's algorithm to find HCF of 4052 and 12576. We have studied what is Euclid's algorithm. The first step of Euclid algorithm says that you need to apply Euclid's division lemma for the given two numbers. Okay, what is Euclid's lemma again? Euclid's lemma is if you have any two numbers a, b, then it is you can write your a in the form of a is equal to bq plus r, where q and r are unique and 0 less than or equal to r less than b. Right? So here I'll apply Euclid's lemma to our given two numbers like this. Okay, 4052, and I'll perform the division like this. So I think 4052 3 times will go. Let's check. 4052 into 3. 3 2s are 6, 5 3s are 15, 3 1, 4 3s are 12. Yeah, 1256. 3 times 1 2 1 5 6. Subtract 6 minus 6 0, 7 minus 5 2, 5 minus 1 4. Then if your remainder is not equal to 0, then you need to apply again division lemma to the obtained remainder and the divisor, previous divisor. Here the previous divisor is 4052. Then I'm applying again Euclid's division lemma. So if I'm writing first step, no, Euclid's division lemma 4052 and 12576, if I apply division lemma, then I can write my 12576 as this form, in this form, this first step, right? 12576 equal to 4052 into 3 plus 420. This is the divisor, this is the coefficient, and this is the remainder. That's what Euclid lemma says. That is what I have written here. Okay, the second step would be applying lemma to again 420 and 4052. I think it will go 9 times. Let's check. 9 2s 18, 4 9s 36, 37. Yeah. 9 times 3780. If I subtract 2, 15 minus 8. What is 15 minus 8? 3, 5, 6, 7, 7. 10 minus 7 would be, no, here 9 will be there, no, 272. Yeah. Then here again not equal to 0, then again we have to apply. Before applying, first we will write this in the form of Euclid division lemma. So how can I write 4052 is equal to 420, our divisor, into q, which is 9, plus remainder 272. That's what written here, step 2. Okay, let's perform step 3. 272, 420. It won't go 2 times. It will be more than 420. 272 once per 272. If you subtract 10 minus 2, 8. 12, not 12, 11 would be there. 11 minus 7, 4. 3 will be here. Then 1. 3 minus 2, 1. Again not equal to 0. We'll write this in the form of this. 420 is equal to 272 into 1 plus 148. That was our third step. Now again 148, 272, will again apply the lemma. 2 times it will be more than this. So I'll take 1 time, 148. 12 minus 8 would be 4. Here 6 will be there. 6 minus 4, 2 and 1. 124 and 148. So here also you can write 272 is equal to 148 into 1 plus 124. Again not equal to 0 remainder. So again applying the lemma. Once 124, 8 minus 4, 4, 4 minus 2, 2. Of course this again we can write like this, 148. And again apply the lemma. 24, 124. Oh my god, this is going so long. 24, I think 24 5s how much? Let's see. 5 4s 20, 5 2s 10, 11 12. Yeah, 5s 120. Remainder is 4. Again 24. 4 how much? 4 6 are 24. 6 are 24. Finally, the remainder is 0. So last step is 24 is equal to 4 into 6 plus 0. The remainder is 0. So the divisor in this step is 4. So the divisor here in the last step is 4, which is the HCF of the given two numbers. Therefore, the HCF of the given two numbers is 4. Okay. Let's see the next problem. Show that every positive even integer is in the form of 2q and that every odd integer is in the form of 2q plus 1, where q is some integer. Okay. So what do we need to prove here? Every even integer is in the form of 2q. Odd integer is in the form of 2q plus 1. Of course, we will use Euclid's division lemma, which states a is equal to bq plus r, and of course 0 less than or equal to r less than b. Here if you observe, this is in the form of bq and bq plus 1. So I'll start doing like this. Let a be any positive integer, and here I can see that it is in the form of bq and bq plus 1. I'll suppose my b as 2. Let's take b is equal to 2. Then if you apply Euclid's algorithm, it will be in the form of a is equal to bq plus r, where here b is equal to b equal to 2. So this will be in the form of a is equal to 2q plus r. And we know this condition on r. R must be less than b, strictly less than b. But here b is equal to 2. So r must be less than 2. Then what are all the possible values of r? R is equal to 0 or r is equal to 1. R can never be 2 because r is less than 2. Okay. So our a is in the form of 2q plus r. So if r is equal to 0, a is in the form of 2q. If r is 1, a is in the form of 2q plus 1. We know that any even integer is in the form of 2 into something. Here, the something is q. So, if a is in the form of 2q, then a is an even integer, right? Because it is in the form of 2q means it is even. And if you add plus 1 to any even integer, it would be odd. So, if a is in the form of 2q plus 1, it would be odd. That's what they have asked us to prove, no? Show that every positive integer is in the form of 2q, that every positive odd integer is in the form of 2q plus 1, right? That's what we have proved, hence proved. Okay. Next question. Show that any positive odd integer is in the form of 4q plus 1 or 4q plus 3, where q is some integer. Again, I'll start doing by taking let a be positive integers, and here as I can see, it is in the form of bq plus r, bq plus r. I will take my b as 4, right? B as 4 and a be any positive integer. Then our a will be in the form of a is equal to b is 4, no? bq plus r, 4q plus r. Since we know that 0 less than r less than b is here 4. So r can have values r is equal to 0 or 1 or 2 or 3, but not 4 because r is less than 4, right? So r can have all these values. Suppose if r is equal to 0, our a will be in the form of 4q. If r is 1, a is equal to 4q plus 1. If r is 2, a is equal to 4q plus 2. If r is 3, a is equal to 4q plus 3. Here if you see, if a is equal to 4q we can write it as 2 into 2q, which is in the form of 2 into something, so it is even. We don't, so r cannot be in the form of a equal to 4q. If a is our odd, a is here, if a is equal to 4q, it is even, so a cannot be in the form of 4q to be an odd integer. Again here also, if I take 2 common, 2q plus 1, it is in the form of again 2 into something. So if a is in the form of 4q plus 2, it will become an even integer. So a cannot be in this form. Here 4q plus 1, 4q of course you can write it as 2 into 2q plus 1. 2 into something even plus 1, it will become odd. Okay, so a can be in the form of 4q plus 4 in order to be an odd integer. Again, 4q plus 3. Here also you can write 2 into 2q plus 3. 2 into something is even plus 3. Plus 3 means it will become odd. So this is also odd integer. So if a is in the form of 4q plus 3, it will be an odd integer. That's what they have asked us to prove, no? If a is in the form of 4q plus 1 or 4q plus 3, where q is some integer, then it is a positive odd integer. Hence proved. Right? Then next question. I think this is the last example in this exercise. A sweet seller has 420 Kaju Barfi and 130 Badam Barfis. She wants to stack them in such a way that each stack has the same number and they take up the least area of the tray. What is the number of that can be placed in each stack for this purpose? So this sweet vendor has 420 Kaju Barfi and 130 Badam Barfi. And she want to place them in a tray such that Kaju Barfis are also having same number of stacks. Then Badam Barfis also having same number of stacks such that they take the least area on the tray. Since each stack has same number. See, each stack has same number. So we need to find the highest common factor for these two numbers, right? So then only they will take the least area, no? If you take any random number, it might not take least area. If you take the highest common factor of these two numbers only, it will occupy the least area on the trace. Okay. So finding HCF 130 and 42. First step, of course, Euclid's lemma. Apply Euclid's lemma to 130 and 420. The first step would be 130, 13 3 is 39. No, so you can take 13 3 is 39. 0, 12 minus 9 would be 3. Here, of course, remainder is not equal to 0. So again, we need to apply Euclid's lemma to the remainder and the previous divisor, which is 130. 130. 3 3 is 9, 3 4 is 12, 120. Okay. Again, the remainder is not equal to 0. Apply again Euclid's lemma to the remainder and previous divisor, 10 and 30. 10 3s are 30. Yay, we got remainder 0. So the previous divisor was 10. This is the HCF of the given two numbers, 420 and 130. So if the sweet seller stack them in a way like 10, the sweet seller can make stacks of 10 for both of the burfis so that they occupy the least area there. 10 for both kinds of burfis. So that's it for this video, guys. So I will see you in next video. Until then, bye bye.